All right, so we were talking about the force of gravity or the gravitational force of attraction. One piece that I didn't say here is it actually has another name that we'll get to. Okay? All right, so we were talking about Newton's universal law of gravitation, which is this equation. And it tells us that, he tells us that any and every two objects in the universe with mass exert a gravitational force of attraction on each other. And we can calculate that force of attraction by using the masses of the two objects measured in kilograms, the distance from the center of one object to the center of the other, and it's center to center because even though our centers aren't far from our edges, the Earth's center is. Okay, so center to center. And G is a universal constant. It's so it's called the universal gravitational constant. Okay, I should probably put the word gravitational in there. Universal gravitational constant. And universal means it is the same everywhere, whether you're on the surface of the Earth, in the International Space Station, on the surface of the Moon, on your way to Jupiter, no matter where you are, this value does not change. G is equal to G is equal to 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay? Now, all of this I'm telling you is because we're leading to something. So don't stress too much about what we're doing. By partway through tomorrow's class, all shall be well. Okay, but this is the universal gravitational constant. Okay, 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared. If you look at the units, then when we put the units in our equation, they're going to get multiplied by two masses, which will cancel out the kilogram squared on the bottom, and you're going to divide by r squared, which will be meters squared, which will cancel out the meters squared on the top, which will then leave us with newtons, which is what force is measured in. So we always pick the units on our constant to make sure that they work out. Someone said to me once, that's cheating. And it's like, no, that's being smart. Why would I put the units to be something that didn't work? Okay, so capital G then is the universal gravitational constant, and this is what it's equal to. And so then Fg is the gravitational force of attraction between the two objects. Gravitational force of attraction between the two objects. And it's a force, so it's measured in newtons. Now, if you look at this equation, just as a little aside, is called an inverse square law. And when you go on into grade 12 physics, you'll see it in electricity, and when you go into science 12.2, you'll see it in there. It's known as the inverse square law. And I say that only because what we have discovered actually, let me explain it first. What we mean by inverse squared law is that the force varies inversely with the distance, right? So the smaller the r gets, the bigger the Fg will get. The bigger the r gets, the smaller the force will get. So it varies inversely. But it actually varies inversely by the square of the r. So if I double r, make it 2 times bigger, then Fg is going to get smaller, but it's going to get smaller by a factor of 4. So inverse, this one gets bigger, that one gets smaller, but the squared means by a factor of the squared. So if I make r a third of what it was, so I make it smaller, Fg will get bigger by a factor of the third squared, so by a factor of 9. Okay? And I say that only because when scientists are doing research and they're measuring things and trying to figure out an equation to fit it, they get really excited if their data begins to match what's known as an inverse square law, if one varies inversely with the square of the other, because they show up a lot in nature, in things in nature, like the force of gravity. And so when we find data that matches this equation now, we're like, ooh, we must be on the right track. We must be doing the work correctly. Okay, so that's the inverse square law. And so again, if you double R, F will get smaller by a factor of 4. If you halve R, F will get bigger by a factor of 4, etc. All right, I'm trying to decide if I think I want to stop there. I want to leave the example with it for class when you're with me in class, just because I think it will make more sense. Okay, so this is enough of an introduction, and the first thing we'll do in class when I see you is we'll use this to calculate the gravitational force of attraction between two people in the room. Okay, just to get a sense of how to use it so that I can continue to explain how we're going to use it this semester. Don't be scared by its form. We're going to simplify it before the end of tomorrow's class, I promise. Okay, so no homework with this one tonight. Your homework is to finish that half sheet and to work on number 18 from the displacement velocity acceleration sheet, like I explained in the next video. Okay?